Hi dear students, we were discussing on the Platoon diffusion and Boltzmann's like travel behavior or traffic flow behavior. So this is the third part in this series of lectures. So in the previous two videos we have seen what is a Platoon, we defined a Platoon, and on what are the parameters or the characteristics that we can use to define this Platoon. And then in the previous video we have seen the Platoon ratio and the Platoon dispersion. And today we will be discussing on the Platoon dispersion models. Okay, so let's move on to that. In today's video, I'll be mostly discussing on the Platoon dispersion models. So in the previous video, we have seen how this Platoon dispersion is taking place. So we have a sequence of signals coming in a corridor or sequence of intersections with signal control in a corridor. We need to know how this Platoon dispersion happens as the Platoon moves from one signal head to the other or from one intersection to the other, how this Platoon dispersion happens, which we can simulate using models. Okay, so Platoon dispersion models, it simulate the dispersion of a traffic as it travels downstream. So this we can estimate by knowing two things. So the vehicles are reaching at the downstream side from the upstream intersection, right? So first of all, we need to know the vehicle arrivals at downstream based on the vehicle departure from the upstream intersection. Okay, so we have to have the upstream vehicle departure profile. So the vehicle that is reaching at the downstream intersection is dependent on the upstream vehicle departure profile. So those vehicles which are actually departing from the previous intersection is reaching the next intersection. So if you want to know how much is the flow or how much is the arrival rate at the next intersection, we need to know how much vehicle has already departed from the previous intersection. So that is what is given here. The flow at the downstream or the arrival rate at the downstream end, it depends upon the vehicle or the upstream vehicle departure profile. Again, we need to know how much is the time taken to reach this downstream end. So for that we have to have an idea about the traffic stream speed. So the time taken for the vehicle which has departed from the previous intersection to reach the next intersection, that we should know. The time required to cover this much distance. Again, that depends upon the traffic stream speed. So the distance is a fixed one, right? The distance between the two intersections, it's a fixed quantity. And again, how this travel time varies? The travel time varies with respect to the traffic stream speed. So the Platoon dispersion model, it simulates the dispersion of traffic stream as it travels downstream based on the vehicle arrival at the downstream end, which is actually a function of the vehicle departure at the upstream location, and it also depends upon the desired traffic stream speed. So there are two models, or there are two mathematical models. Two kinds of mathematical models have been used to describe this dispersion of Platoon, and they are Robertson Platoon dispersion model, that is a widespread model which is being used for this study of Platoon dispersion. So there are two kinds of mathematical model. One is based on the normal distribution assumption. So that is a normal distribution model which is proposed by Parsi, and another one is the geometric distribution model which is proposed by Robertson. So the Robertson's Platoon dispersion model, which has become a virtually universal standard Platoon dispersion model, and it has been implemented in various traffic simulation softwares also. So from the various studies that has been done, it is found that this Robertson model is reliable for modeling the traffic movements in urban street networks, and most of the results shows that the Platoon dispersion that is predicted by the Robertson model is reliable, accurate, and robust. So because of these findings, Robertson's model is universally accepted to study the Platoon dispersion. Okay, so again, once more I'll explain the Platoon dispersion. Uh, the Platoon dispersion of the Platoon from one intersection to the next, it depends upon the departure rate from the previous intersection, and also it depends upon the travel time required to reach the next intersection. Okay, so that is the basic idea of Platoon dispersion model. Next we will see the mathematical model or the model structure to explain the Platoon dispersion. In the previous class, we discussed about the Platoon dispersion or the concept of Platoon dispersion. So we have seen there in this figure also you can see here there are two intersections and the direction of flow is also given here. So the traffic is moving in this particular direction. So the top one can be called as the upstream, from where the vehicles are departing, and the next intersection where these vehicles are arriving at, it can be called as the downstream intersection. So you have an upstream and a downstream intersection. So as the vehicle move through this defined distance between this upstream and downstream, so what happens is like the platoon of vehicles that is leaving from the upstream intersection get dispersed. So it can be due to various factors. One is due to the distance it has covered. So some vehicles may speed up, some vehicle may slow down. So because of which this platoon dispersion can happen. So it is because of the friction between the vehicle, and again because of the land use pattern by the side of the road. Okay, there may be parking, there may be bus stops, there may be side roads coming and meeting here. So because of this because of the interference from the roadside boundaries or the roadside friction also can create dispersion. Okay, so dispersion, we can say it's a function of the travel time from a signal to a downstream signal, and again it depends upon the length of plateau. So longer the distance to be covered between the signals, the greater is the chance for dispersion. So we have explained this figure also. So when it leaves from a particular intersection, it is the plateau, the peak is high, whereas the length of plateau is less. But as it moves downstream, what happens is the peak of the plateau, it reduces, whereas the length of the plateau, it increases. We are trying to model this platoon dispersion with the help of Robertson's model. So what I can give you is the Robertson's model, so which is given by, so this actually models the dispersion at the downstream, or the dispersion or the dispersion that is happening at the downstream side. It again depends upon the flow at the downstream. Okay, so the basic Robertson recursive platoon dispersion model is given by this mathematical form. So what do you mean by recursive? Because it is some kind of repetition is happening there. So here, what is the left hand side? Q dt. Okay, so Q, it always represents a flow. Usually it represents a flow in traffic engineering perspective. So Q dt, so the superscript d, it represents the downstream end. So I can say the Q is the flow. So the flow at the downstream intersection, okay, at time t, at any time t. So the left hand side in this equation is the flow at the downstream intersection, or the downstream signal at time t. It's the left hand side which we are going to model. So this becomes our response variable, okay, which depends on what all factors. I can say there are two terms here which is added up here. So the first term and the second term. So let me first of all explain the first term. Here you can see a factor Fn. Fn is a soothing factor that I will explain later. Then what is this next term? So the flow at the arrival at the downstream side, it depends upon the vehicles that has already departed from the upstream end. So this Q, again it is the flow. And what is this T minus T? Okay, so T minus T, it actually represents the departure flow rate. For Qt minus t, it's a departure flow rate at the upstream signal at time t minus t. So for example, if you want to model the downstream signal at time t, then we have to take the departure flow at t minus t. What is this capital T then? T is the travel time required to cover this much distance. So the flow at the downstream end at time t is dependent upon the departure rate from the upstream end at t minus t, where capital T, it is the minimum travel time required to cover this link. Okay, it is measured based on certain factors. It again depends upon the travel time factor and also the average travel time. That I'll explain what is beta and TA. TA is the average link travel time and beta is the travel time factor. Okay, and what is N? N is the modeling time step duration. N is the modeling time step duration. So I told you here there are two terms. The first term is actually giving you an idea about the profile of the upstream intersection, or the profile of the departure at the upstream intersection. So that is given by the first part. And there is again the second term. Okay. So what is the second term? Second term is again QD into QD T minus N into 1 minus F. Okay. So this term, let's define what is this particular term now. So as I told you, the Q superscript D, it is representing the downstream flow at T minus N. So we are modeling it at every simulation time step. We can consider that to be N. So we are modeling it at every N. Okay, nth time. So this I told you, Robertson's Platoon dispersion model is a recursive one. So we will be actually getting the input from the previous time step. So that will also get added in order to get the response at the present time step. So that is what is given here, the second term. The second term actually explains the traffic flow from the previous time step. Okay, that I can explain to you with this diagram. So this graphical representation of the model is given here. It clearly shows that the predicted flow rate at any time step is a linear combination of the original Platoon flow rate in the corresponding time and the flow rate of the predicted Platoon in the previous time step immediately preceding it. So since the dispersion model gives the downstream flow at a given time interval, the model needs to be applied recursively to predict the flow. So that is what is given by this thing. So I can see it is actually representing the inflow of vehicles at the downstream end. So it's not only the present inflow, the output we are getting here now. So that get added to the next time step. So it is actually a recurring process. So it again depends upon the flow that is departing from the previous intersection or the upstream intersection, and again if we are modeling it, we have to get this the arrival rate or the arrival rate predicted at the downstream end from the previous time step also need to be added here. So that is why it is called a recursive model. It's kind of repetition, we have to add this up. Okay, and here Fn, it is a smoothing factor. Fn, it is considered as a smoothing factor, which again depends upon two things. So the Platoon dispersion, it depends upon two factors. One is based on the travel time it covered, and also depending upon how much dispersion is taking place between the vehicles. So this Fn is a smoothing factor, which again depends upon the Platoon dispersion factor alpha n, the travel time factor beta n, and Ta, again it's the average link travel time. So we may be knowing the average link travel time, and if for every Platoon if we need to calculate, so we can use this average link travel time to get the actual travel time between the two nodes. Okay, so this is Robertson Platoon dispersion model. So it depends upon two factors. Okay, two things we can use here to explain. So it first of all depends upon the flow that is departing from the upstream intersection, and also it depends upon the flow, okay, or the predicted flow from the previous time step. predicted flow at the downstream end from the previous time step. So these two added together will give you the flow at the downstream end at time t. Hope the concept is clear to you. Let me explain these terms: alpha, beta, t, etc. We are discussing the Robertson's Platoon dispersion model. I told you it is a recursive model. Okay. What do you mean by recursive? Because if you want to predict something, okay, the prediction at the current time step, it depends upon the prediction from the previous time step also. Or if you want to predict something at the present time step, you have to input the prediction at the previous time step also into the current model. Okay, so that is why it is called the recursive kind of model. Okay, and again it follows the geometric distribution. So what do you mean by geometric distribution? So geometric distribution, it represents the number of failures before you get a success in a series of Bernoulli trials. Okay, so geometric distribution, it represents the number of failures before you get a success in a series of Bernoulli trials is what is a geometric distribution. So for example, you are going to a polling station and you are conducting some exit poll there. So you are asking the people like to whom they voted for. So you wanted to get the people who voted for the Z candidate. Okay, so for that you have to ask every person, so who voted for the Z candidate. The geometric distribution would represent the number of people who you had to poll before you found someone who voted for the Z candidate. So for that you would need to get a certain number of failures before you go to your first success. Okay, so that is what is the geometric distribution all about. So the Robertson Platoon dispersion model is defined as, or it is actually the weighted combination of the arrival pattern at the downstream end of the link during the previous time step. So which is given by this one, the second part of the equation. Okay, so it is the weighted combination of the arrival pattern at the downstream end of the link during the previous time step, and also the departure pattern from the upstream traffic signal at t-1 second k. So this is the Robertson's Platoon dispersion model, and then Seddon, he developed a numerical procedure for doing this. Okay, so the Seddon developed a numerical procedure for calculating the Platoon dispersion, and the equation is given here. So it's actually a repeating process. You have to sum the values at each previous time step value in order to get the prediction at the next time step. So that is what is given here. So if you are predicting the flow at the downstream end, in order to get the flow at the next time step, you have to get the flow from the previous time step. So these are the various time steps given here. So in order to get the flow at the second time step, you need to get the flow from the previous time step, and also you need to know what is the departure flow rate that is happening. Okay, T is the time taken to cover this, capital T is the time taken to cover the distance between the two intersections. Okay, and again there are two terms here, beta and alpha. Okay, so beta and alpha, they are dependent on each other. So beta represents the travel time factor, which we can use to find what is the actual travel time between the nodes, or the actual travel time required to cover the link. Okay, so beta is known as the travel time factor, and alpha is the Platoon dispersion factor. Okay, so they are dependent on each other. You can write this beta to be 1 minus 1 plus alpha, or alpha is 1 minus beta by beta. Okay, so let's define the terms alpha and beta now. So using the basic properties of the geometric distribution, we can derive the calibrating, we can derive for calibrating the parameters of Robertson's Platoon dispersion model, like this: beta is equal to 1 by 1 plus alpha, or alpha is equal to 1 minus beta by beta. And alpha and beta, they are the calibrating parameters of Robertson's Platoon dispersion model. Okay. Where alpha is the Platoon dispersion factor and beta is the travel time factor. So beta and alpha, I told you, these two factors, they are dependent on each other. That is the travel time factor beta and the Platoon dispersion factor alpha, they are dependent on each other, because the Platoon dispersion happens as the travel time increases, or the distance to be covered increases. The Platoon dispersion also increases. They are dependent on each other. So usually we assume a factor of 0.8, but we can calculate that by using this equation. So once the standard deviation of link travel times is given to you, and also if you know the average travel time from which you can find this travel time factor. So the travel time factor, it depends upon three parameters. One is the average travel time in that link, or the average travel time between the two nodes or the intersections. It again depends upon the time step for modeling, that's n. It also depends upon the standard deviation of the travel time on the road stretch. So if you know these three factors, you can find beta n. Okay, so beta n, or the travel time factor at the modeling time step n, it depends upon the average travel time in that link, and also the standard deviation of link travel times in that road stretch. Then next, when these are given to you, you can again find the certain factor. It again depends upon the time step modeling n, and also the standard deviation of link travel times sigma. Okay, so this can be, if these two factors are known, you can calculate the smoothing factor or smoothing factor directly from the standard deviation of the link travel time and the time step of modeling. So if these two values, beta n and fn, they can be mathematically determined as long as you know the average link travel time, time step for modeling, and the standard deviation. So this is all about the Robertson's Platoon dispersion model.